Let's solve another Leetcode problem today. And today we are going to solve problem 235, lowest common ancestor of a binary search tree. So this is one of the problems in the blind 75 list. And by solving this problem, we can actually get some unique insights about how to approach a problem, how to do some conversations with the interviewer. And these are the key things like we should remember before we solve any problem. We should ask all the kind of constraints, what interviewer has in his mind. So not only that, we will actually revisit some of the characteristics of binary search tree. So before that, let's see what is the definition of the lowest common ancestor. Okay, so according to the Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T, which is T is the binary search tree, that has P and Q as descendants. Okay. Okay. So here, let me show you one example. So this is how a lowest common ancestor looks like. So suppose this is a binary search tree anyways, right? Okay, so this is node A, this is B, this is C, this is P, this is Q. If someone asks what is the lowest common ancestor of P and Q, then you see B is the actually common ancestor of P and Q, right? So B is the answer. Now, obviously, A is also a common ancestor of P and Q, right? For P and Q, you see A is also a common ancestor, but we want the lowest one. So A is in top, like say level 0, B is at level 1, right? So we want the lowest level, like the one that is the nearest. Okay, so there goes it. So here the lowest common ancestor is B. Okay, so let's look at the example here. We're given a binary search tree here, and two nodes, P equals to 2, Q equals to 8. So that means we need the common ancestor of 2 and 8, right? And you see the common ancestor is 6. Okay, so there goes the first example. Now let's look at the another example. You are given a binary search tree where P is 2 and Q is 4. So that means we need the common ancestor of this and this. Okay, now the thing is, here in the description, we said like we allow a node to be a descendant of itself. That means if I look for if a node can be a descendant of itself, in that case, we can say that 2 can be a descendant of 2. So the lowest common ancestor for 2 and 4 are 2. Okay, so the answer here is 2. This node is the lowest common ancestor. Okay, so this was, before you solve the problem, you should always ask. So there might be chances that the interviewers are not going to tell you this, like if any node can be a descendant of itself. So you should always ask, like, can I just suppose in these cases, suppose one node is a parent of another one, right? So the given two nodes, one of them are the parent of the other one. In that case, can one of the nodes become the ancestor of the both of the nodes? Yes, in that case, your interview will clear it up to you that, okay, yes, a node can be a descendant of itself. Okay. Other questions that you should have, like before, you should clarify this in not only in this interview, in any kind of interview. Say, are you sure that P and Q both are present in the tree? Okay. Are you sure about that? Can you tell us? Like, or there might be cases that one of these are not present. Obviously, valid question. Another question is, can P be equals to Q, right? Right? Is that possible? And obviously, the other question was like, if P and Q has a parent-child relationship, right? What happens then? Now, for the third one, we already asked the question and we got the answer from here, right? In that case, we allow one node to be a descendant of itself, any node to be a descendant of itself. So whatever is the parent node is going to be the lowest common ancestor. For the first two questions, let's see the answers. Like the constraints for these problem are like P cannot be Q. Yes. So what my question was, like, are P and Q both present? Yes. P and Q will exist. Yes. So this is the answer to that question. So if the answer is say no, we cannot say for sure if both P and Q are in the tree. In that case, the solution is going to be different. But in this particular case, we are making sure, or the interviewer is making sure that P and Q both exist in the tree. The other thing is, our next question was, what if P and Q have the same value? Well, the answer to that is these two. Like we know that all nodes are unique and P cannot be equals to Q, okay? So all those things are now cleared up. Okay, so good that we had some clarifying questions. Now let's try to solve this problem. Okay, so before we solve this problem, let's think about some scenarios. Say, for the binary search tree, we know that we can say that for a binary search tree, we know that the condition is like if we have a, say we have a left subtree here, right? And we see the root value 6. So we can say that anything here is less than 6, right? Anything is less than 6. Okay, now for the right subtree, we can say anything here is greater than 6, right? Okay, so we know this. Okay, now here is the thing. If we reach, like, obviously we are going to traverse this tree, right? We are going to traverse this tree using any traversal mechanism. Say we can do a DFS, right? And if at any point we see that the node that we have reached, the node that we are traversing now, is equals to P, or the node, so we are given, okay, the node that we got, okay, so sorry, node's value, right? If the node's value is equals to Q, if that is the case, if we have reached a node that has a value of P and Q, in that case, we can say just return the node, right? Because we have reached one of the values. And so, suppose for this example, right? Once we are traversing at one point, we may reach this node 2. And we see that the value of the node actually matches P, right? We can immediately say, okay, then we have reached a node. So this is going to be the common ancestor. Okay. Okay, so that is one case. And let's talk about another case. So suppose you have reached a node, and then you see that node dot value is greater than P, and node dot value is less than Q, right? That means you have reached a node. Say you reached this node, and then you see that the node's value is greater than P. That means P is here, right? So can we say that P is, or let's draw this, say somehow, okay. So somehow I reached, somehow I reached this node, right? And then there is some like other things here and there, okay? That is fine. Okay, and then after reaching here, I find that this is my left subtree, and this is my right subtree. Okay, so I have reached this node, say, this is my node, and I see that my node's value is greater than P. That means where is P? Then P must be somewhere here, right? In the left subtree. And the node's value is less than Q. Then where is Q? Q must be in the right subtree. Right? Can we say that? In that case, can we say, oh, okay, we have reached a node where P and Q have made separate divisions, like one goes to the left and one goes to the right. Now, can I say, okay, now this node is actually the common ancestor? Can you say that? Of course, right? We can say that. This is from the characteristics of binary search tree. Okay. Same case is like this, or the opposite. Node dot value might be less than P and node dot value is greater than Q, right? Yeah, the same thing. So this or this, right? Okay, so we got our two of the things, and then yeah, so let's try to code this. Okay, okay, now let's talk about the third thing. Like, so 1, 2, I'm writing the third one here. The third case is I have reached a node. After traversing, I have reached a node. That is fine. Now I see that node's value is greater than P. And node's value is greater than Q. Right? It's greater than both of them. So what can I say now? Can I say that, so suppose I have reached this node, right? This is my node, and I see the node's value is greater than both P and Q. Can I say now that if my node's value is greater than P and Q, that means both P and Q are here, both of them here, because my node's value is greater than P and Q. That means P and Q are in its left subtree, right? So in that case, can I call, say, lowest common ancestor function on the node's left value, left child and P and Q, right? So now I can just search in this area, right, for P and Q. Okay, that's the case. Or can we say that if node's value is less than P and then node's value is less than Q, in that case, I know that both P and Q are in the right subtree, right? Must be in the right subtree. So we can't call the lowest common ancestor with node dot right, and then we pass P and Q. So basically I start searching again for the lowest common ancestor inside my right subtree. Okay, so those are the cases. Now the code. So let's check the code. I already have coded it. So you see, obviously if I have, so I am using it as a recursive function. And if I do recursion, I can actually traverse the tree as DFS. So you know in DFS what we do is we call the tree with left subtree and then again with right subtree, and then we also do some of the operations here, right? Okay, so I am checking, currently I'm in root, like any node. If the current, think this as a current node, right? We start at the root node, but eventually we're going to traverse the tree and go down, right? Okay, so if the current node's value is equals to P's value, or the current node's value is equals to Q's value, so I have reached any of the values, then I can immediately say, okay, this itself is the lowest common ancestor, because from the definition we say like any value can be a descendant of itself, right? Okay, and then else if the current node's value is greater than 1 and less than the other, or is greater than the first one and the less than the second one, right? Okay, so in that case, this is a point, this node is a point where P and Q actually are divided into or located into two subtrees, one in left subtree, one in right subtree. In that case, root is the lowest common ancestor. Done. Else if root's value is greater than P value, okay, then and obviously I didn't write this. I could just write this. This is more clear. Greater than Q. Why didn't I write this? Because okay, so because this must be true, it cannot be like this is not possible because I already have checked this part here, right? Since this was not hit, that means this is no longer possible, so obviously this is also true. Okay, I can just write this to make it, yeah, let's write this. So if root's value is greater than P's value and greater than Q's value, then I search in my left subtree, because P and Q both are in my left subtree. I'm calling the same function. Otherwise, that means if root's value is, or current node's value is less than P's value here, and also less than Q's value, then I search for P and Q's lowest common ancestor in the right subtree. Okay. Okay, so let's try to submit this. And you see this one got accepted, and this one was pretty fast. And here we have done, say, we have done basically DFS, right? So we did DFS here. So that means we visited each node once. So in that case, we can say that the time complexity is order of n, and the space complexity we know for DFS is also order of n, because if you are doing recursively, then we are building a call stack, and in the worst case, we'll be going down like n steps. Okay, so that's it. Thank you very much for watching. We'll come back with another